Welcome to part 2 of the breeding value prediction module of the TLR course at the University of Pretoria. In this second part, we will mainly just look at the construction of the mixed model equations and how these matrices are then constructed and utilized and in a very simple example, utilized for the prediction of the genetic merit of animals, farm animals. Just a quick reminder of the construction of the mixed model equations as we ended at the first module. These are the mixed model equations. This is our coefficient matrix here. The biggest matrix here is our coefficient matrix. We also have a column vector of unknowns, the unknown effect of the environment or the fixed effects like the sex effect or the herd year season effect or the age of dam effect or whatever the different fixed effects are or environmental effects. The unknowns we are really interested in would be the additive genetic merit or the additive value or the breeding value of each of these animals. So the number of rows in this column vector would be on the top part, the B values would be then each row for each fixed effect or level of a fixed effect, and then a row for each animal where the breeding value predictions would then be calculated. This is our right-hand side. Our right-hand side basically consists obviously of the same number of rows. The fixed effects will have the same number of rows, and this will be the summation adding up each of the levels of the observations per fixed effect. So if we have two sexes at the top, we will add up all the weights. If this is weights that we're calculating the breeding values for, add up all the weights of the female calves, one big sum, all the weights of the male calves, and if we have, for example, 3 levels of 3 farms or 3 tests, if it's a growth test, we will just simply add up all these weights or these average daily gains, or milk if it's dairy cattle, or fleece weights if it's sheep, woolen sheep, and so forth. And then at the bottom on the rest of this column, Z prime Y would be the actual observations of each animal. So if an animal weighed 215 kilos at weaning, and this is weaning weights that we predict breeding values for, there will be a 215. If the animal was not weighed, let's say it's a parent who wasn't weighed as such, then it will simply have a 0 in that column or that specific row for that animal. So that is what our right hand, we call this a right hand side, and this is then the column vector of unknowns that we want to predict. So the big part then is the construction of our coefficient matrix, and there are each of these are submatrices. So x prime x is a submatrix, x prime z and z prime x, they are basically mirrors of each other. So you will have a diagonal running down here, and z prime x prime z and z prime x will just be mirrors from each other. So x prime x is simply telling us how many observations there are per contemporary group or per fixed effect. So if we take the example that we just used up till now, can be a different one, but let's use the example where we have 2 sexes and three farms with male and female calves at each farm. So you end up on your diagonal at the very first element in that on that diagonal will be the number of observations of sex 1. Let's say we have 13 females. There will be a 13 in that very first element on the diagonal. On the next element of the diagonal would be the number of male calves, and the next one the number of calves in herd 1, then herd 2, then herd 3. So this is basically a square matrix with the dimensions of the number of levels of the fixed effects. If we have 2 sexes and 3 farms, then it will be a 5 by 5. If we have 2 sexes and we have 6 farms, so it's 6 plus 2, it will be an 8 by 8, and so forth. So that will just give us the number of animals with observations in each of the levels of the fixed effects. So that's a square matrix. X prime Z would link each animal to its correspondent fixed effect. So if it's a female calf, it will have its for all the females will have basically a row there, and the males in the next row, and then each of the other fixed effects will have a row, and it will simply link each of these animals, because an animal will also have a column Z prime Z. We'll get to that. It will link each animal to a specific fixed effect. For example, if it's a female, her equation will link. There will be a 1 in this corresponding element, and obviously a 0. She can't be male and female, and she will be observed in one of the 3 farms. So in the farm that she has an observation, there will be a 1 in the element, and the rest will be zeros, and so forth. When we do the example, it will be much clearer than this. This is exactly the same. So a female animal will have an equation. So she will have her own column going right through. There's an observation, there's a breeding value that's unknown, but it will also link her here to a fixed effect. First the sex, then maybe the farm she was observed in, and then if she has a recording, a Z prime Z, there will be a 1 on the diagonal. If she did not have a recording, there will be a 0 on the diagonal. So Z prime Z is basically an identity matrix that links an animal to an observation. So it's a matrix, a square matrix, and on the diagonal we will basically have 1s for the animals with observations. A minus 1 is a very, very special matrix. It's the inverse of the A matrix. Now the A matrix is the additive relationship, the average numeration relationships matrix. So it's how much animals are related to each other, but the inverse of that. So we know, for example, that 2 full SIPs will be 50% related, to half SIPs 25%, and so forth. So we have a square matrix where all the animals will be part of that square matrix, and on the diagonal would be the 1 plus the inbreeding coefficient, and on the off diagonal elements each animal will have a row and a column. So in the off diagonal elements would be the true relationship or the additive relationship amongst the animals. So, but this is the inverse. And then alpha, if you can look at the definition of alpha, alpha is basically the total variance divided by the additive variance, or if we write it differently, it is 1 minus the heritability divided by the heritability. So alpha is basically telling us how much of the differences amongst these animals are due to additive genes, the 8 square. If we go to the very first example, I think it will be much more clearer to you how these matrices are constructed. Let's just use a very, very simple example where we only have 5 animals. They are obviously males and females in this case, and these animals are we have birth weights recorded for them, and we would like to predict the genetic merit or the breeding value for birth weight for these animals, but not only for these animals, but also for their sires and dams. So let's say, for example, these 5 animals were the progeny of 3 sires and 3 dams. So one could ask the question, what is the effect of sex of the calf on birth weight, corrected for genetic differences or additive genetic differences? So this is what we call the blue, the best linear unbiased estimate of the fixed effect. So we will have a corrected effect for the sex of the calf, whether it's female or male. But we also would like to know the blood breeding value for each animal. So it's our 3 sires and 3 dams plus our 5 animals. So we will get solutions for each of those animals. So each animal, 3, 6 plus 5, will have its own equation, and we have the same number of unknowns. So we need to use matrices to solve all these equations for us. Okay, so this is just another way of dealing with this. This is a simple table of our observations. So we have our 5 animals. Let's call them animal 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5 animals. These are our 5 animals. The first animal, animal number 4, is a male. The next 2 would be females, and animal 7 and 8 would be males again. So these, we have 2 females and 3 males. Remember, we basically have 2 levels of fixed effects, male and female, in this very simple example. Animal 4 sire is sire 1, and its dam is unknown. For some reason the dam was not recorded, so the dam is unknown. Animal 5 sire is animal 3, and its dam is animal 2. This same dam is also the mother of animal 6, and the sire is again sire 1. Animal 7, the dam is animal 4. Can you see there is animal 4? It's also the dam of this animal, and the sire of this animal. It's a male, sorry. It's the sire of this animal, and the dam is animal 5. And animal 8, the sire is animal 3, and the dam is animal 6. So it's obvious that if we draft our A matrix or our additive relationship matrix, that we need to take in consideration that these animals are actually very much related to each other, and we have to take that into consideration. None of sires 1 and 3 were recorded, measured for birth weight. Neither dam 2 were recorded. So if we construct the coefficient matrices, we need to take that in consideration, that they have no observations. And obviously we have one unknown dam here as well. So the actual weight of animal 4, it's a male calf, was 45 kilos at birth. The actual weight of animal 5, 29, animal 6, 39, animal 7, 35, and animal 8, 50. So we have our so-called right-hand sides here, where we have the animal equations. So let's start. Oh yes, before we start constructing the matrices, the additive variance for this trait is 20 kilograms square, and the total variance is 40 kilograms square. So we can then calculate alpha. We said alpha is sigma square E on sigma square A. That's 40 on 20, and alpha in this case is 2. Okay, so we have alpha. We have the relationship amongst these animals if we use this part. We have the 2 levels of the fixed effect, and we also have the actual weights of these animals, all the right-hand sides. So we can start constructing the very first square matrix. Remember, we had 2 levels, 2 sexes, so this will be a 2 by 2. We had 3 males and 2 females. So we will never have elements in the off diagonals except 0. So 3 males, 2 females. If we had 2 more farms, for example, and we had 1 animal in farm 1 and 4 animals in farm 2, then on this diagonal we would have had an extra 2 levels, and that would have been not a 2 by 2 but a 4 by 4 matrix. So this is always a square matrix. It's also always a diagonal matrix. Number of animals with observations, number of animals with observations on the different levels of the fixed effect. So that's the way x prime x is being constructed. So we can also talk about the observations per fixed effect or per contemporary group. The next matrix that we need to construct is z prime x, and here we have animal 4, 5, 6, 7, and 8 had observations. 4, 5, 6, 7, and 8 had observations. So the bottom part of this would be, there's a column for males and a column for females. So the bottom part here would be a 1 for animal. It is a male, so it has an observation in the male column. The next 2 animals were females, so they have 1s in the female column, and the last 2 animals will have 1s in the male column. I must actually warn you that there's a part missing, and that would be our first 3 animals on top, and they will simply have zeros in both columns because they do not have observations. Again, remember that this is an incomplete matrix, and we still need to have columns for the parents without observations here at the top, and they will have zeros in both the columns. So animal 1, 2, and 3 will basically have zeros running along on these two columns. So this is basically then a matrix where we linked observations to specific contemporary groups of fixed effects. And then we have the transpose of the previous matrix, exactly where we had columns, now we have rows. So there's animal 4, 5, 6, 7, and 8. And remember, this is an incomplete matrix. There's also a column for animal 1, 2, and 3. But since they do not have observations or measurements, they will only have zeros in these rows. So animal 4 had an observation. It was weighed, and it's a male, so it's in the male row. Animal 5 and 6 were 2 females, that's why they have 1s in the female row. And animal 7 and 8 were males, that's why they have 1s in the male row. Remember again, it's not a complete matrix yet. We need to add columns for animals 1, 2, and 3, but since they have no observations, they will only have zeros on these 2 rows. So basically, x prime z is the same as z prime x. It's just a transpose of each other, and it's also linking observations to fixed effects or contemporary groups. Good, then that brings us to our next square matrix, and that is z prime z. So here we have a column and a row for each animal. So that's animal 1. Remember, it did not have an observation, it wasn't weighed. Animal 2 did not have an observation, it wasn't weighed, that's why it's only zeros in these columns. Animal 3 did not have any observations, that's why it only has zeros in these columns. But they also have rows. That's a row for animal 1, that's a row for animal 2, and that's a row for animal 3. And you will see only zeros, no observations. Animal 4 was the first animal with a weight, with a birth weight. That's why on the diagonal it has a 1. The same with animal 5, 6, 7, and 8. So it's basically a diagonal matrix with ones on the diagonal for those animals with observations. Otherwise, there will be a 0 on the diagonal. So that's a very simple matrix to construct. It's basically just a matrix of zeros and ones with ones on the diagonal for those with observations. So this is basically an identity matrix where the observations are being with ones on the diagonal. Good, then we have to construct the A matrix, and that is the additive relationship amongst the animals. So I'm not going to go into very fine detail, but what I would like to show to you are a few things. Each animal again has a row and a column. So animal 1 is related to itself 100%, a1. It is the parent of animal 4. That's why it has a 0.5 or 50% relationship with that animal. It's also a parent of animal 6, 50% relationship. It is a half sip of animal 7 and a half sip of animal 8. That's why it's got a 25%. That's just a rounding error. So it's 25% related to each of those animals. So animal 7 is 25% related to animal 1. It's also 50% related to animal 4 and 50% related to animal 5 because it is its two parents, and so forth. So here you also see there's a basically 12.5% relationship where you have half sips and so forth. So, or quarter sips and so forth. So this is then the construction of matrix A. But as you saw previously in our coefficient matrices, we need A minus 1 or the inverse of A. So this is an additive numerator relationship matrix. It's square, it's symmetric. So you have ones on the diagonal, and that is the relationship of an animal with itself, and it's actually 1 plus the inbreeding coefficient. So if an animal is 25% inbred, it will be 1.25 on the diagonal. So it's the diagonal is 1 plus the inbreeding coefficient on A. And on the off diagonal elements is the relationship of the animals amongst the animals. And this is square and it's symmetric. What you get here at the top end here, right top end of the diagonal will be exactly the same as the bottom end below the diagonal. Okay, so we have seen in the previous module when we dealt with matrix algebra or basic calculations of matrix algebra, it's then possible to calculate the inverse of A. Remember the inverse of A, the definition of an inverse is if a matrix is multiplied by its inverse, it gives you a matrix of the same order, a square matrix, and with ones on the diagonal. Okay, so this is then the inverse of A, and we then need to multiply the inverse with alpha. Alpha is a scalar, so it's a simple way of multiplication. Each of the elements are then multiplied by alpha. In our case, remember, our case alpha was equals 2, so each of these elements were then multiplied by 2, and this will then give us A inverse alpha. We need to add z prime z that we just constructed with this newly calculated inverse of A multiplied by alpha. So this black part here at the bottom is then this square matrix, z prime z plus A minus 1 alpha, and that is that part. Remember, we constructed z prime x prime x, 3 males, 2 females. We also, these are 3 animals without observations who did not have weights. The column of the first animal, second animal, third animal, or the row of the first animal, second animal, third animal, animal 1, 2, and 3. And then from animal 4 onwards, we could link them to one of the two. This is a male, 2 females, and 2 males again. And the same in the columns, we have a male, 2 females, and 2 males again. So x prime z, z prime x transposed of each other, and then we first constructed z prime z, where we had ones on the diagonal for those animals with recordings, and zeros on the diagonal for those animals that did not have recordings. We constructed A, which on the diagonal gave us ones, which means the relationship of an animal with itself. It's a 1 plus the inbreeding coefficient. We constructed that. We got the inverse of A. We multiplied it with alpha. Alpha is 1 minus h squared on h squared, or sigma squared E on sigma squared A. We multiplied, and that's a scalar. We multiplied it with the inverse of A. We added those two matrices together. They are of the same order, so we could do that. So we ended up with this square matrix here at the bottom. And this big matrix then is what we call our coefficient matrix. So we have then constructed our coefficient matrix as part of the mixed model equation. Good. We had the coefficient matrix on the one side. We have the unknowns. We have 2 levels of our fixed effects. We have sex 1 and sex 2. So we still don't know what the real effect of sex 1 and sex 2 is. And then we have our animals, 1 to animal 8. Remember, the first 3 animals did not have observations, but they do have equations. And then the rest, 1, 2, 3, 4, 5 animals had weights. And here you can see their weights on the right hand side. So we have a column vector here. At the bottom end, the first 3 animals did not have weights, so we have zeros there. And then the first animal, animal 4, weighed 45 kilos. The next one, 29, 39, 35, and 50. So this is the bottom end of the column vector. And then the top end, we added up. Remember, we summarized the weights of sex 1. So we added up all the males, and together they weighed 130 kilos. And we did the same for the females. Together they weighed 68 kilos. So basically we ended up with our mixed model equations, coefficient matrix, the big one, x prime x, x prime z, z prime x, z prime z plus a minus 1 alpha, coefficient matrix. We ended up with our 2 levels of our fixed effects. We have our random effects, unknown random effects, the additive effects, and we have our right hand sides. At the top, the summation of all the male calves weights together. The 3 animals together weighed 130 kilos, and the 2 females together weighed 68 kilos. The first 3 animals did not have weights, they are only parents, or they are parents, and then the rest of the animals, each of their weights are being each has its own row or element in this column vector. So this is our unknowns. These are our unknowns. This is our coefficient matrix, and this is the right hand side. To enable us to get solutions for B1, B2, and A1 to A8, we need to get the inverse of the coefficient matrix, multiplied by the right hand side, and that will give us a column vector. Remember, the number of columns in this and the number of rows need to be equal to enable you to multiply. So you get the inverse of this, you multiply it with the right hand side, and you end up with a column vector, that would be the solutions for B1, B2, A1 to A8. So again, that's our x prime x, x prime z, the transpose z prime x, z prime z plus a minus, or the inverse of a, times alpha. This is B, the unknown two levels of B1 and B2, and we have our additive, or A hat, our prediction of our breeding values. The right hand side, x prime y, that's adding up those two, or the weights of those two sexes, and z prime y, the first three animals did not have observations, and then each animal's weight as we go along. So the solutions then, once we've multiplied the coefficient, the inverse of the coefficient matrix with the right hand side, we end up with solutions. So for sex 1, the effect of male, the fact that this is a male, is 43.72 kilograms, and female, the effect of female, 34.04 kilograms. So this is the blues, best linear unbiased estimates for males and females. That's the, call it the environmental effect or fixed effect on this, corrected for possible genetic differences amongst those animals. Then we also get solutions for each of these animals. So our first animal, who was only a parent, not weighed, had a breeding value of 0.98 kilograms. The next one, minus 0.19 kilogram, and so forth. From our fourth animal, we had observations, so this is very close to 0, and obviously you see that this animal will give you the lightest scores at birth, irrespective of sex, because this is an unbiased prediction where the effect of sex is already out or not being considered in your breeding value prediction, irrespective of sex. And you will see this is a deviation from 0. How much heavier or how much lighter will be the progeny of these animals as parents? That then brings us to the end of part 2 of our breeding value prediction module of TLR at the University of Pretoria. We have looked at how we construct the mixed model equations in matrix format, and we then used these constructions in matrix calculations. We have seen that the most important sources of information that we needed would be the relationship amongst the animals. So we need to know the parents of the animals. We also need to know the actual recordings or observations on the animals within contemporary groups. In this example, we just use 2 levels, sex levels, male and female, as our fixed effects. And we also need to know what the additive variance is in relation with the total variance, or the H square, the heritability. And we basically use that to construct some matrices, a square matrix that tells us how many animals had observations per level of fixed effect, x prime x. We also looked at linked each animal to a specific fixed effect, because each animal has a row and a column in our coefficient matrix. Also those animals without observations, and obviously they cannot be linked to a fixed effect because they do not have an observation. So they basically in their columns or rows will only have zeros, but the animals with observations will have ones in the corresponding level of the fixed effect, and zeros obviously in the other levels. It's either sex 1 or 2, or if we consider herds, for example, an animal will only have an observation in one specific herd. Then we constructed Z prime Z. Z prime Z is basically linking an animal to an observation. So it's a diagonal square matrix, and on the diagonal will be a 1 in the corresponding row and column of a specific animal where the animal has an observation or a measurement, and a 0 on the diagonal where it does not have an observation. and so we constructed Z prime Z. We also constructed A, which is the additive numerational relationship matrix. So how much additive genes do family members have in common? That because we basically work with additive genes, we need to work with the average additive relationship amongst these animals. We constructed that based on the fact that we know that, for example, that full SIPs would be 50% related and so forth. On the diagonal, it's a square matrix because each animal will have a row and a column. So if we have 50 animals, it will be A will be a 50 by 50 matrix. And so on the diagonal will be a 1 plus the inbreeding coefficient of the animal. So if the animal is 5% inbred, it will be 1.05 on the diagonal. And then the off diagonal elements where a row and a column, that element in that row and column corresponds with two animals, will be the additive relationship between those two specific animals. We then needed to get the inverse of A minus 1, and A minus 1 is then multiplied with alpha. And remember, alpha is sigma square E on sigma square A. That's multiplied and that's added to Z prime Z, that matrix that link observations with observations on animals, or whether they have measurements on that not. So that then concluded our coefficient matrix, the big matrix, which is basically a square matrix with the dimensions, all the animals plus the levels of the fixed effects. That will be the order of that matrix. Then we have a column of that is multiplied by a column of unknowns, and the first two rows, or the first rows in our unknowns, would be the levels of our fixed effects. If we only have two levels like sex1 and sex2, there will only be two rows. If we have, let's say we have 5 more herds, then it will be 5 herds plus the 2 sexes. That will be 7 levels, 7 rows in our column vector. And then each animal will have an element in the rest of that column vector, because that would be the unknown additive value or breeding value of that animal. And that equals our so-called right-hand sides, and the first columns in our right-hand side will be the summation of the weights or the observations measurements of each of these levels of our fixed effects. If we have, for example, 2 levels of fixed effects, sex1 and sex2, we simply add up those weights, if it's weights of the animals in sex1, and that would be our first element or row in our column vector, and the other level will be the next one. If there's 5 more herds, for example, we will have 5 more rows in that column vector. And then it starts with animal 1 and it ends up with the last animal in that row vector. Once we have constructed that, we need to get the inverse of our coefficient matrix, and that is then multiplied by our right hand side, and then that will give us a new column vector with the same number of rows as the different, or the number of levels of the fixed effects, and also each animal will be represented in a row. And that will be our solutions. The top part, the solutions for our fixed effects, we call blues, best linear unbiased estimates of the fixed effects, and each animal's additive value we call BLUP, breeding values, best linear unbiased prediction of the value of the animal as a parent. That then concludes part 2, and we will follow with part 3.